In this round of astronomical billiards, later, Uranus will plunge on past Neptune, leaving the nearby planet group and turning into an interstellar shuttle in the enormous scope of the universe. Mankind has continuously tried to push the limits of investigation to uncover the secrets hidden inside the profundities of the universe. For more than 40 years, one rocket has epitomized the eager interest and steady quest for information, Explorer 2. However, recently, Explorer 2 has made a discovery so serious that it is now turning around, constrained by a power beyond our comprehension. What could this revelation be, and what does it uncover about the mysteries of the universe? Join us on this journey past the edge of the universe as we unwind the secrets of Explorer 2's new unnerving discovery in a key moment of human effort. In the midst of the background of 1965, the universe saw the introduction of an exceptional chapter in space exploration. Leading the charge was Gary Flandreau, an illuminating presence among NASA's unit of brilliant minds positioned at the Jet Propulsion Laboratory. Flandreau's task was, however, as risky as it seemed, new, to put together the trajectory of a spacecraft bound for the far reaches of our solar system, where the gas giants, Jupiter, Saturn, Uranus, and Neptune, stood as enticing secrets waiting to be unveiled. Equipped with little more than a reliable pencil, a symbol of precision engineering during a time before digital dominance, Flandreau embarked on his mission. His careful computations and brilliant observations soon bore fruit in the form of a discovery that would rethink the boundaries of space exploration. Diving into the archives of celestial mechanics, Flandreau identified a cosmic ballet set to unfold in the late 1970s and mid-1980s, a fascinating arrangement of the gas giants, a grand celestial movement hidden for centuries. This arrangement promised a celestial exhibition, with the planets forming a majestic necklace with Earth at its center. However, the significance of this arrangement extended far beyond its visual wonder. It introduced a remarkable opportunity for spacecraft navigating the solar system, as each giant orbited in concert, creating gravitational highways, a heavenly slingshot effect that could propel a spacecraft from one planet to the next, reducing travel time and conserving precious fuel. Flandreau's computations revealed not only the potential to abbreviate the journey to Neptune but also uncovered a phenomenon known as gravity assists. This process involves using the gravitational pull of planets to slingshot a spacecraft, boosting its speed while conserving fuel. The specific positions of Jupiter, Saturn, Uranus, and Neptune, when aligned in a certain configuration, created a sort of celestial highway, significantly decreasing travel time between Earth and Neptune. NASA's decision to swiftly capitalize on this opportunity was proof of its agility and determination, even in the face of monumental challenges. The launch of Explorer 1 and Explorer 2 marked not only a milestone in space exploration but also a victory of human ingenuity and perseverance. What's truly remarkable is the longevity of the Voyager spacecraft, designed with durability in mind. Equipped with instruments capable of withstanding the harsh conditions of space for decades, despite being launched in the late 1970s, their technology continues to operate, albeit with some limitations due to aging equipment. As Voyager 1 and Voyager 2 continue their journeys through the universe, they have become ambassadors of humankind, carrying messages from Earth, golden records containing sounds and images representing the diversity of life on our planet. These records serve as a time capsule, a depiction of humanity's collective identity, waiting to be discovered by any intelligent beings they may encounter in the vastness of space. Their mission has far exceeded expectations, providing valuable insights into the outer reaches of our solar system and beyond. Each day, they send back data that expands our understanding of the universe, reaffirming the importance of space exploration and unraveling the mysteries of existence. Initially planned for just 4 years, the interstellar Voyagers embarked on a monumental journey that extended far beyond their intended lifespan. Launched in 1977, the Voyager spacecraft became adaptable wayfarers, surpassing all expectations and rewriting the textbooks of planetary science as they traversed the depths of space. Voyager 1 and Voyager 2 provided humanity with extraordinary insights into the outer realms of our solar system. These bold probes captured stunning close-up images of Jupiter's swirling storms, Saturn's magnificent rings, and the intricate landscapes of their diverse moons, from the icy waters of Enceladus to the volcanic eruptions on Io. Each discovery revealed a dynamic and complex universe that challenged our understanding of planetary cycles. Voyager 2, in particular, etched its name in the annals of space exploration by becoming the first spacecraft to fly by Uranus in 1986. Its encounter unveiled a mysterious ice giant enveloped by an atmosphere of hydrogen, helium, and methane. Just 3 years later, Voyager 2 made history again as it passed by Neptune, providing humanity with its very first close-up look at the distant blue planet and its enigmatic moon, Triton. Yet, perhaps the most remarkable aspect of the Voyager journey lies in its resilience. Despite traveling over 14 billion miles from Earth, the spacecraft continued to communicate with scientists, sending back significant information about the interstellar medium it now traverses. These iconic space probes, reminiscent in size of a Volkswagen Beetle, have exceeded all expectations and continue to push the boundaries of human understanding of the universe. The extraordinary voyage of the Voyager probes began with a challenging gravitational assist from Venus, a maneuver previously never attempted by any spacecraft. This decision exemplified the innovative spirit of the mission, setting the Voyagers apart as true pioneers in the realm of space exploration. Navigating through the vast expanse of space was no easy feat. The margin for error was extremely thin, with deviations measured in mere minutes, highlighting the precision required for such interstellar travel. Numerous careful efforts were made to ensure every aspect of the journey was meticulously planned and executed. As the probes embarked on their journey toward Jupiter, they traveled multiple times farther from Earth than the closest planet. Mercury, their way, driven them through the troublesome space rock belt, a district of space loaded with incalculable divine bodies, each representing a possible danger to the mission's prosperity. This excursion through the space rock belt was a subject of extreme discussion and presumption among researchers and specialists in the 1970s, as the specific thickness and creation of the belt were not completely perceived at the time. In spite of these vulnerabilities, the previous Trailblazer 10 and 11 tests pioneered a path through the as far as anyone knows thick space rock belt unblemished, demonstrating that such an excursion was for sure conceivable. This accomplishment not only illustrated the strength of the space apparatus, but also prepared for the progressive Explorer missions. However, the difficulties for the Explorer tests were a long way from over. As they wandered further into the universe, they experienced various snags and secrets, each presenting new opportunities for revelation and development. With a mere 69 kilobytes of memory, barely enough to store a small picture document by today's standards, the Explorer shuttle faced a gigantic challenge as they set out on their venture. Their memory capacity was the same as a small part of what the ordinary PDA can hold, featuring the extraordinary imagination of the architects who designed them. These gutsy travelers depended exclusively on their locally available insight to navigate the vast region of space before the time of distributed computing and fast web. The information gathered by the instruments on board was stored on old 8-track recording devices, the same sort of tapes grandparents may have used to pay attention to music in their vehicles. Believing that is awesome, such obsolete technology was reliable for saving the significant scientific discoveries made by the Explorer missions. Regardless of their limited resources, the Explorer rocket communicated with Earth using a transmitter that was about as strong as a fridge light. However, with the assistance of giant 12-meter-wide dish radio antennas, they managed to send and receive signals across the enormous field of space. Imagine being so distant from home that it takes over 18 hours for a message to arrive at its objective. That is the reality of the signals sent by Voyager 2 as it wandered further into the universe. Each piece of information, each picture, each murmur from these far-off Voyagers had to navigate unfathomable distances before arriving at the eager ears of researchers back on Earth. As the journeys traveled further from Earth, they had to battle with interference from every kind of human-made gadgets, radio broadcasting music, TV shows, and the unending jabber of mobile phones. Regardless of facing various impediments, the explorers have opposed the odds and continue to amaze space experts with unforeseen revelations. Their excursion through the interstellar void has not only reworked our cosmic playbook but has also adjusted our understanding of the unknown domains of space that extend far beyond our solar system. One such puzzling event is the perplexing Oort cloud, a divine gathering of comet-like elements kept intact by the gravitational pull of the Sun, extending most of the way towards the closest star. It remains a far-off and enchanting domain, and the explorers are slowly but steadily advancing towards it, hoping to unlock its secrets and understand its role in shaping the architecture of our planetary system. Anyway, the excursion through interstellar space, where the solar wind phenomena give way, offers a more open front for investigation. Here, the heliopause marks the boundary between our local planetary group and the vast region of interstellar space, signaling the start of unfamiliar territory. It's a district where the influence of our Sun wanes and the infinite power of the interstellar medium begins to initially assert itself. Estimations of the heliopause distance were conflicting, with some proposing it to be around 50 astronomical units. This uncertainty provoked a surge in funding for the Voyager mission, as researchers sought to unveil insight into this vital boundary. However, as the shuttle withdrew from this milestone, researchers were astonished to find no expected signs of interstellar travel. This surprising revelation has sparked serious discussion and led specialists to rethink current models of interstellar space travel and the dynamics of the heliosphere. In addition, the explorers have also provided significant information on the composition of the interstellar medium, contributing insights into the cosmic environment beyond our planetary system. This data has transformed our understanding of the universe and opened up new avenues for exploration and discovery. As the explorers continue their journey into the unknown depths of space, they embody humanity's voracious curiosity and constant quest for knowledge, pushing the limits of what we think is possible and revealing the secrets of the universe, each revelation in turn. One of the highly anticipated events scientists were eagerly awaiting to confirm in our journey into the unfamiliar domain of interstellar space was the abrupt surge in highly energetic particles known as cosmic rays. These particles, often originating from cosmic explosions and other cataclysmic astronomical events, travel at speeds approaching the speed of light. While these cosmic rays represent a significant danger to spacecraft and, indeed, even human astronauts, most lower-energy particles are actually redirected by the massive magnetic shield created by our Sun's heliosphere. This shield serves as a protective barrier, safeguarding our inner solar system from the majority of external cosmic threats. As the Voyager spacecraft continued their extraordinary journey into the interstellar medium, researchers were not only observing the increase in cosmic rays but also examining any changes in the prevailing magnetic field. This magnetic field is influenced by the ionized gases saturating interstellar space and the nearby stars. The assumption was that this magnetic field direction would vary from the magnetic field within our heliosphere. Despite these assumptions, the Voyager probes reported no observable changes in the magnetic field as they ventured further into interstellar space. Is a surprising realm, and its perception has confused specialists, adding to the mystery surrounding the investigation beyond the limits of our planetary group. On August 25, 2012, Voyager 1 accomplished a notable achievement by puncturing through the heliopause, the outer limit of the heliosphere, the vast bubble of charged particles and magnetic fields created by the Sun's solar wind. This advancement marked the first time a human-made object ventured into interstellar space beyond our solar system. Voyager 1's journey to the heliopause spanned a stunning distance of over 14 billion miles from Earth, demonstrating human ingenuity and the remarkable capabilities of space exploration technology. As it traversed this unknown domain, Voyager 1 continued to send significant data back to Earth, providing insights into the conditions at the outer reaches of our cosmic neighborhood. Researchers eagerly anticipated the arrival of Voyager 1's transmissions, hoping to gain new information about the characteristics of interstellar space. They expected to observe a noticeable increase in plasma density, a measure of the concentration of charged particles, as Voyager 1 crossed the heliopause. However, what bewildered them was the absence of any significant change in the direction of the surrounding magnetic fields, which had been expected to shift as the spacecraft moved from the influence of the Sun's magnetic field to that of the broader interstellar medium. Fast forward to November 2018, Voyager 2, the twin spacecraft of Voyager 1, embarked on its mission to the heliopause. Like its predecessor, Voyager 2 crossed vast distances and sent back valuable data to Earth, enhancing our understanding of the outer limits of the solar system. Despite the anticipation and excitement surrounding Voyager 2's arrival at the heliopause, researchers found themselves again perplexed by the data it relayed. Much like Voyager 1, Voyager 2 detected no significant changes in the direction of the magnetic fields, challenging existing theories and leaving scientists grappling with new questions about the nature of interstellar space. These remarkable missions by the Voyager spacecraft not only expanded our knowledge of the universe but also highlighted the limitless possibilities of human exploration beyond the boundaries of our home planet. Yet, none of the current models could explain the intriguing discrepancy observed when Voyager 2 reached its objective. The solar wind, a steady stream of charged particles generated by the Sun, was found to be at its strongest. This surprising observation implied that the boundary of the heliosphere, known as the heliopause, could extend much farther than previously estimated, potentially beyond the 120 astronomical units originally expected. As the Voyager probes journeyed further into the unknown region where the solar wind meets the interstellar medium, they uncovered a wealth of intriguing information. Among the discoveries were subtle but significant localized changes occurring near the heliopause. These variations appear to be influenced by the complex interactions between the heliosphere and the surrounding interstellar environment, shedding light on the dynamic nature of this boundary region. Despite the intricate changes observed on a smaller scale, the Voyager probes identified remarkably little variation in the magnetic field at great distances. This revelation puzzled researchers, raising questions about the spacecraft's eventual departure from the turbulent boundary zones. Would they ultimately break free from the heliosphere's grasp and encounter the true magnetic field of interstellar space? Debate among specialists intensified, with some hypothesizing that the Voyager probes might still be within the heliosphere, while others pointed to compelling evidence suggesting their entry into interstellar space. This evidence included a significant increase in the detection of cosmic rays, as well as plasma density, indicating a transition into a new cosmic domain beyond the Sun's influence. Addressing this puzzling riddle surrounding the heliosphere is akin to interpreting the intricate dynamics of a goldfish bowl from the perspective of the fish inside. To gain a comprehensive understanding, researchers recognized the need for an interstellar probe capable of providing a valuable external view of this intriguing boundary region. Amid the rapid advancement of technology, the Voyagers stand as remarkable relics of space exploration history, crafted with creativity and foresight. These interstellar trailblazers are propelled by a unique blend of rare engineering and timeless innovation, venturing into the cosmos with instruments tracing back to the 1970s. The Voyagers possess a certain charm that captivates the imagination, their durable frames house instruments designed with precision, each component meticulously crafted to withstand the rigors of space travel for decades. Despite the passage of time, these instruments continue to operate with astonishing effectiveness. The power source of the Voyagers is equally fascinating. Utilizing the heat generated from the radioactive decay of plutonium, these spacecraft convert nuclear power into electrical energy, an engineering achievement that has sustained them for over 50 years.